Hello, everybody. I'm starting. We welcome you today at a tinyML meetup talk in Grenoble, France. My name is Irina Sizova. I'm a digital marketing manager in Green Waves and the organizer of today's tinyML discussion. Today, with me in the office is my colleague Francesco Pacci, who will be a moderator of our talk. I will give him a floor a bit later to present our speaker. In
Hello.
Green Waves, Francesco is an R&D software engineer and in charge of driving machine learning applications on our ultra-low power processor. We organize these webinars every 2 months and receive honestly quite good positive feedbacks from the audience. So please don't hesitate to comment, send us email on the topics you would like to hear. We're definitely interested in that. The main objective of these events is, of course, to support the ultra-low power machine learning community, bring together business and academics, and expand the tinyML ecosystem. Traditionally, at the beginning, I have to thank all the sponsors who made this initiative possible. Aeon Devices, ARM, DeepLight, EMSA, Green Waves Technologies, Groovit Incorporated, Edge Impulse, HOTG, ImagineMob, Latent AI, Maxim Integrated, Analog Devices, Kixo, Qualcomm, Reality AI, Renesas, SAP, Seed, SenseML, SynSense, Syntian. Several slides just to mention incredible events that happen in tinyML community. So November 16, the tinyML organizers had a really interesting workshop. Please have a look on the website. There was an event, tinyML Asia. Please also go to the website to find out more information about that. And the winners of the tinyML Vision Challenge are also announced on the website. So there are a lot of interesting things happening in tinyML community. So website is the right referral to go. The next, by the way, webinar topic would be in December 1st on open source AI framework for any hardware. At this moment, Francesca, I will give a floor to you to present our speaker today.
Yes, thank you. So we welcome today Anna Petrovicheva. She is in computer vision industry since more than 10 years, and she is part of the OpenCV Foundation, and she's CEO and founder of Experience.AI, where she works to deliver AI complete solution for a wide range of applications from medical to sport and education. So I leave the floor to her, and she will give a talk on enabling vision for low power devices. So thank you, Anna.
Thank you for the introduction, and thank you for joining, everybody. So first, I'll talk a bit about myself and my career in computer vision to give you some perspective on why I'm interested in this stuff. I've started doing computer vision back in 2010. Then it was a classical computer vision. I was developing a part of OpenCV computer vision library since then. At some point of my life, I switched into high performance computing and machine learning applications, and I spent 2 years developing them at Intel. Then I decided to get back to my first company that is called ITSYS, where we again developed OpenCV. But 2 months from that, ITSYS was acquired by Intel. So I got to Intel the second time in my life. I spent another 2 years there, and in 2017, me and my 2 colleagues, my fellow engineers I was working with for a lot of years by that point, we decided to open our own consulting and product company that is called Experience.AI, where I'm the CEO up until now. So at Experience, we basically work with teams worldwide to create low power computer vision based solutions based on neural networks. And as Francesco said, we apply it for many different industries, from medical to sports and entertainment to autonomous driving and many different other industries. I'm also a part of OpenCV. I'm now a member of OpenCV board. You may wonder what is a board of an open source computer vision library, but yeah, we have a board where we take some strategic decisions. And I'm also a part of OpenCV community that is big and covers a lot of different communities, research laboratories, companies all around the world. So you probably know about OpenCV, but I'll say a couple of words about it still. So OpenCV is the biggest computer vision library in the world with up to 2 million downloads every week only in Python distribution. And OpenCV is used everywhere, almost on every smartphone, in space, underwater, and basically in almost any place where we have some computing machines on Earth. So this is OpenCV. Now I will move to my topic, which is about artificial intelligence on the edge devices. And first, I will share my view through my kind of biography why artificial intelligence is moving to the edge. So obviously, like I separate three biggest reasons why I see the customers wanting to move to the edge devices from the server computing. It's like edge devices are very close to consumer. Obviously, everybody here knows what is the edge devices, but I'll still say a couple of words about it. They are very close to the consumer. It is smartphones, wearables, stationary cameras, and very, very low power devices from the Internet of Things world. So they can be either powered by some power outlet or more typically by battery power, where now they can live several years on the same battery. So the progress is moving there very fast. So why we are moving to the edge devices? First, the first reason is there is no need to send the data from the edge device and back. So the data is captured somewhere close to the user, for example, in the camera, and there is no need to spend some internet traffic to send it somewhere to the server, local server, or maybe remote server in some cloud facility. The second reason is the server costs, because even though it's very, very convenient right now, and cloud solutions have been growing like crazy in the recent years, they are very costly, and it actually can be a significant part of a company's budget to pay for AWS. So when computing on the edge device, you basically save on these server costs a lot. And in some cases, there is a more kind of pressing issue of security and privacy, where this can be a showstopper to applying some artificial intelligence-based technologies. So in corporate environments, for example, it is not an easy thing to send out imagery taken at the workplace somewhere else, because it may contain some confidential information, documents, or even faces of the employees. Same goes to the privacy protection laws, right? Privacy protection laws in Europe, Brazil, China, and other countries, they basically say that you cannot just send visual data, including like private information, like the image of the face and your location. You cannot just send it without user's consent, which means that you need to process all the data and extract all the analytics from it right close to the place where the data was captured without sending it over the internet. And this is basically moves us to the requirement to port artificial intelligence algorithms to the edge devices. My idea is that it's not a new movement in computer vision and basically other industries too. During my career, which started in 2010, I saw a loop of the interest to the edge devices, and I expect this to happen at least once more. So when I started computer vision, I was doing classic computer vision on the edge devices. It basically was the time when we tried to port, as we thought, very complex computer vision algorithms to mobile phones and even smaller devices like FPGAs, and try to make them as energy efficient as possible, while retaining the same accuracy and quality that we had before. So we worked with a lot of companies from like both big companies and small companies, because it was a boom there. To like some algorithms in computer vision definitely were working there, and people needed to get them close to their customers. But in 2012, it suddenly appeared that the state of the art of computer vision suddenly moved a lot, thanks to AlexNet and this very, very famous work from the research lab of Geoffrey Hinton. And closer to 2014, there were already some applications in computer vision that were ready for the production use. And they were basically using neural networks. They gave a significantly higher quality than we were getting with the classical computer vision algorithms before that. So in 2014, we could not implement these algorithms on the edge devices, both because there was no software and no hardware that would support that. And deep learning and computer vision got back on the servers because we needed a lot of computing power to compute even like object detection problem on an image or video feed. So this was this way from for approximately up until 2016, when there started appearing some. Actually, there was a boom of startups that were talking about creating neural networks accelerators and some devices that would allow to process neural networks on the edge devices. They were not mature at this point, but it started then and it continues up until now. So artificial intelligence is moving back to the edge devices for all of the reasons that I discussed before. And this is a huge trend now. So most of the customers I work with, most of the companies that I see in this industry, they are interested in the inference close to the user, not far away in cloud computing systems. Obviously, I'm a very biased person because I work in this area and I talk with specific people and they support my view of the world because they are from the same kind of world. But I'm pretty sure that this is the case for the whole industry, not only kind of the small part I'm seeing with my two eyes. So in the future, I see two important trends. First, there are two technologies that are long awaited, at least by myself, but I do believe that they will happen with us in the next decade, which is artificial and virtual reality and metaverses. And the second is robotics. My own view on robotics is like when I started computer vision in 2010, I was actually thinking that in 10 years from now, we would really have robots working, helping us in our mundane activities. But we still don't have them even now, which is a sad thing for me. But I really, really hope that in the next decade, we'll finally have robots helping in our lives. And these two industries, artificial reality and robots, they do require a lot of computer vision and neural networks to be done correctly. For example, in artificial reality and virtual reality, you need to recognize the surroundings of the person, recognize the obstacles, recognize the gestures that they are showing to the camera to manipulate the interfaces. In robotics, obviously, we need to recognize the surroundings too, but we also need to recognize how to manipulate with some objects, for example, with robotic arms. And these are algorithms that cannot tolerate the latency of sending the data back and forth to the cloud and back. So these are two very important areas that will also help develop artificial intelligence on the edge devices, especially extremely low-powered edge devices. On the other hand, 1.5 basically years, the last almost 2 years were there was a transformers boom in the state of the art of computer vision and machine learning. For me, it was kind of the time when everything kind of calmed down. Finally, there was no kind of big breakthroughs for maybe like 2 years in terms of the state of the art of computer vision. And then there are transformers that beat the state of the art in many, many different areas, including classification, object detection, image segmentation. And they also kind of reopened the areas that were not working with neural networks, like image generation by caption. So I believe that this is only a start of the transformers boom. And transformers are super heavy in terms of compute power. So I believe that in terms of transformers, we will have this loop once again. we will first need to depend on the servers and server inference. And I do believe that in 3 to 4 years from now, we will be able to infer them somehow on the edge devices. That's my prediction. We'll see whether I'm correct or not. Okay, so maybe there are some questions. Maybe we can stop here. Maybe there is a number of questions that we can already answer.
We don't have yet, but I have one.
Okay.
So you presented like 3 reasons to move to the edge: the security and privacy, the server cost, and also the fact that you are closer to the user. With your client, do you see with the people you're working on, do you see one which is or you see an order of them, so they move for one more than the others, or so just if you can elaborate on this.
Yeah, sure. So the third one regarding the security and privacy is typically a showstopper. So it's kind of a question of life and death for a new company, for a startup. And the question of the internet traffic and server costs is typically arises at later stages of the development of the company, when they already have some income and some product market fit, but now they want to cut the costs to basically increase the profit. That's what I'm saying.
Okay, thank you.
And Francesca, I also have a question, Joanna. Transformers is definitely a very exciting area in the past year or two. So 2 questions: how small are visual transformers today, and how small do you think they can go to be able to be embedded onto edge devices? What is your kind of prediction there?
So they are incredibly huge, super fat, and I have this feeling about them. Like it feels very similar to what we had back in 2013. We actually were talking in the on our workplaces that we cannot believe that at some point there will be neural networks on mobile phones, and like it was the reality for like 8 years ago, and this is the reality for the transformers now. I do believe that it will take a bigger kind of technology loop to get there, but I do believe that we will get there in like 3 to 4 years right now. And I understand that this is a prediction and I can be wrong, and transformers will be kind of forever stuck in servers. But something tells me that the chances of that are not that high.
Okay, then we maybe can go for another one. We have a question from Mark, which is saying, with respect to transformer, which hardware device or combination of hardware devices do you see bringing transformer networks to edge devices for low-powered AI and ML computing? And then there is a following up. Do you know of any examples of transformers on edge devices?
No, I don't personally know, and I'm pretty sure there aren't at this point. So to get neural networks on the edge devices, there were basically 2 big steps. First was definitely algorithmic in two areas. First was in the architecture of the neural network itself, and the second was in libraries that were able to very efficiently compute the transformations that were inside neural network. So I believe that the software is the first step and the hardware is the second step. And we are not there with the software even yet. So from my point of view, first algorithms, they kind of exhaust the area of applicability, right? So they are first applied to a lot of different areas and show some dramatic progresses there. Then it comes to the optimization of the algorithms. Then it comes to the implementation of tooling, specifically libraries that can infer them. And after that, it goes to the hardware.
Okay, thank you. Thank you. And there were another one on chat, which is if the model is run on the edge, what are some strategies for getting more data for training? I think that maybe you will talk about this a little in the presentation.
Let's keep it.
But yeah, maybe we can keep it for okay.
Yeah. Okay, I will cover my next slide then. So first I'm going to talk, first I was talking about the why of the artificial intelligence on the edge devices. My next part is about the how to make an algorithm that really works. And I will start with, a bird view on the problem, and then we will focus on the software and hardware part. So how to solve a problem? First, we need to understand whether we can solve it or not. And the easiest mental exercise that I always do when I get a new, a possible project or possible problem to work on is I first try to look at the data myself and use my human vision to try to solve it first. So the idea is the following. For example, we look at the image on the left here, and people with sufficient vision capabilities can recognize the numbers on the license plate on the left very quickly, right? It takes me definitely under 1 second. Under 1 second. I cannot measure it more precisely, but definitely under 1 second. Now, for the image on the middle, I cannot recognize the cells here. I do know that this is something about biology, but this is it for me. But an expert in the field would be able to, again, recognize the cells on this image in under 1 second. They are trained for that. They can do it very fast. For the image on the right, if I was asked to detect all the people standing here, I can definitely detect some of the people, but it takes me a bit more time to do that. And for the black area on the image, I'm actually not sure, maybe there are some people or not, I cannot see them. So the idea is the following. If you can look at the image and immediately say the answer, or if there is a person who can look at the image and immediately tell you the answer, it may be an expert or a doctor, then the problem is solvable on the edge. If it is not, if it's not that easy, if you need to, think a bit first, then it's probably not solvable on the edge, even given enough data. So the problem needs to be easy for human to solve. The state of the art on servers, if you're given unlimited compute power, is the following. You are allowed 2 or 3 seconds to think about the image to produce the result. If you need to think about, for example, 20 minutes, then it's probably not here. So, we still cannot render whole movies given a caption. For example, if I say I want to watch something some thriller or comedy for a night, I believe that we will get it at some point, but we are not there, and we will not be there in at least 5 years from now. So, okay, let's imagine that our problem that we want to solve is either is closer to the left or the middle image here, so it's easily solvable by a human. In this case, it becomes a data-bound problem. You need to collect a very diverse, a very big data set that represents the problem in order to solve it. And if you have the right amount of data, the right quality of data, taken with shoot with the same camera on the same typical area or location, and if you have enough artificial intelligence knowledge or background, then you definitely will be able to solve a problem with a very high quality. This is the state of the art that we are living with right now. Moreover, you most probably will be able to port it to a mobile device or an edge device on a battery power in a way that allows you to do the inference in some feasible time. It's a more complex thing. It's not enough to just have a general artificial intelligence background typically together. So it's a very specific of skills that I will talk a bit about later. But still, it's very, very doable problem at this point. So the whole pipeline of solving the task in this case looks the following. You collect the data, then you get the annotation team or go to some annotation service to annotate the data, meaning you give the labels to the objects that you are interested in. For example, if you want to find a bounding box for every person, you will ask the annotators to put a bounding box for every person. There are some specific rules about the annotation. For example, it cannot be subjective. It needs to be very objective, meaning that 2 different people need to do the annotation in a very same way, so that the third person wouldn't be able to recognize who was the annotator looking at the image. I hope it makes sense. So if the problem is subjective, one person thinks one way and another person thinks the other way, then it may be not a very good fit for artificial intelligence. especially if you have a lot of different annotators, because the algorithms, they can just not find the logic behind the different kind of predictions on different images. So when we have annotated our big diverse data set, we will go and train the model. I will talk a bit about this later, but the first hint that you need here, you need to start with a very small model from the start. It's not good to, train a huge fat network and then try to squeeze it into the target device. It's not good. You should start with a very small but well-performing network from the start. And the final step is deployment to the target environment. Typically, the third and fourth step, they are even done by different teams. And I always vote for the team that trains the model to implement tests, because it's really important when you transfer the code from one team to another team that will deploy it to the target environment to be able to reproduce it. Sadly, in our kind of data scientist space, it's kind of okay to write bad code still, but I don't think that it's okay anymore, because even though we are data scientists, we're still programmers, and we need to kind of respect the other teams that are working with our code after we did. This is my point of view. So the target environment typically requires other languages than the ones that the model was trained with. The training part typically happens in Python. Deployment typically happens in C++ or even C, pure C. So this is basically why the need of different teams or people with different expertise. Of course, there are people who can both train a model and port it to the target device. But this is, I would say, becomes less and less common in the industry. Okay, so maybe this is the point when I can again answer some questions if there are some.
Yeah, so I don't know if there is still this one on data. So what it is, how we get, what are the strategies to get more data for training?
Okay, so my recommendation when I start a new project is without knowing the nature of the project, I would recommend to grab 10,000 frames, 10,000 images of as diverse nature as possible, meaning that you need to shoot them. For example, if you were trying to detect people in night conditions, then you would want to place the camera exactly at the place where they would be in the real life, or in similar places, right? For example, outdoors. And I would try to organize the shootings so that they cover different weather conditions. For example, have full moon, have rain, maybe have even snow, right? So that we can cover the whole kind of range of the conditions that we can meet in real life. I would ask different people to appear on the frame in different groups. From 1 to maybe 10 people. If I was organizing the shooting. But the best way to grab data is always the best kind of possible situation if you already have some cameras there, right? And there is some real life going on around these cameras. Just take this real life and don't try to kind of simulate it. Split it into some chunks, try to take as diverse data as possible, and this is it. Is it helpful?
Yeah, it makes sense to me. Yeah. And I also have a question is, do you see any solution? Because I mean, the data, it's not a small problem. So when you start a project collecting data, it's maybe longer and more painful than training and the deployment. So do you see any solution to this manual process of collecting and annotating, or do you see any perspective? Because also, I mean, having data, it's really the key. We know that we have a lot of models. You can maybe sometimes change the model. Is not so much important to the architecture sometimes, but the data, if you have bad data, you won't have a good algorithm.
Yep, exactly. I totally agree with you, Francesco. And there obviously are some solutions for annotating the data. There are some services, and it becomes an industry of like data annotation, a whole industry by itself. But I don't know whether it's definitely not an industry of like data collection for now, because like neural networks, they are pretty, like, they don't have like big enough generalization, which means that if you want to create a solution for a very specific case, you need to be very specific about how you collect the data in terms of the camera, the environment, and stuff like that. So it's still kind of a very, very tiresome process, I would say. You know, it makes me kind of feel better when I work with the customers who collect data. Like the hardest case of like I ever saw in data collection was there is a data set that is called ScanNet. It's a big data set of 3D environments. I personally know its author. Her name is Angela Dye, and when she created this data set, she was at Stanford. She was in Stanford. She was studying. So this data set consists of 3D scans of 1.5 thousand rooms of her friends, colleagues, everybody she could find in Stanford. Can you imagine that? She like did it 1.5 thousand times. She scanned every room she was in with a 3D scanner. I just cannot imagine this effort. Typically, creating data set is significantly easier than that.
Okay, thank you. And so we have another question is there any process for correcting classification in real time? We learn when we get corrective feedback. Is this being done with the AI? So
yeah.
you think that?
So, you know, in my career, I had probably close to 100 people talking about this kind of online learning, but I only saw this implemented once. So this is a system everybody dreams about. The kind of only, I would say, place where it works, and this is kind of the life or death problem again, is there are sites that read capture automatically, right? A capture when you need to kind of automatically recognize the fire hydrants or taxis or some words to enter some site. So there are some sites that do this kind of a questionable thing of automatically recognizing captcha. They need to do this online. In all the other cases, typically, if you train the network correctly on a big enough and diverse data set, you are happy enough with the system that you don't need to go all the way and implement this online learning thing.
Okay. And there is another question which is maybe similar. So is continual learning possible? So it's probably answered by what you said. Then there is a question on if you think that people who train models should also participate in data collection, cleaning, and annotation. So it's probably to learn better what they are using. And I also couple with another one, which is, are there any design patterns and best practices for going from deep learning approaches to tinyML approach?
Yeah, sure. Thank you for the questions, by the way. So yeah, there are, I mean, we are called data scientists for a reason. I believe that data is the most important part, just like Francesco said, of every project that we do. And I definitely vote for data scientists to be the part of the data collection and supervising the data annotation process. The worst situation ever is when a data scientist, like a data team, is already given with their data set and they're not happy with that. Basically, the effort was already spent and they cannot get into they cannot produce a very good model given bad data, but they cannot actually just go and redo all the effort because it's lengthy. So yeah, I mean, it is one of the good practices. So another practice that I already mentioned, I just will mention it once again. Data scientists need to write good code. They need to deliver their work not as IPython notebooks, but rather as packages or libraries with tests. They need to have continuous integration applied to their repos, like repositories. And when they commit code, it needs to be tested. It's super important if you want to to move some algorithm from like state of the art or like algorithmic kind of state into production. It's really important. And this is probably the biggest change, the biggest difference from the between the academia and production. So a good practice that I would also say is when you start doing computer vision or when you join a team, to start a library that you would call some like utility library or internal library with the useful things that you need to train a neural network, because these kind of things, like everybody kind of has their own preferred methods of doing that, and you basically find yourself implementing same code all over again in every project. So I would recommend to kind of pile them up in some like reusable form. Yep, I think this is it.
Okay, thank you. We have another one, which is on the comment on C and C++ from Arnab, which is saying, as per your comment, using C or C++ for implementation of networks on target edge devices, what is your take on HLS versus HDL in terms of deployment on low power and memory constrained FPGAs? As I believe HLS uses C++ and HDL is Verilog VHDL and more oriented toward hardware description. So I don't really know what is referring with HLS. I don't know if you know.
So I know about this, but I'm not an expert in that. So okay. The best way to answer this question would be to talk to my colleague. I can talk to my colleague who is an expert in that and give you this answer in writing. That would be the best way.
Okay.
Thank you.
So I think we can go on.
Okay. So as I said, like when we create a solution that will work on a very, very low power device, we need to think about the both components, meaning software and hardware. I will start with hardware because I'm not a super expert in that and I don't have a lot to say in that. I'm a software person myself, but I can just say that we definitely have seen very kind of amazing things happening in hardware in the last decade. Obviously, most of you know that kind of this whole artificial intelligence boom happened because the GPUs that were created, that were produced by NVIDIA, surprisingly, they turned out to be a very good computing platform for neural network computation, but they were not designed to do that. They were designed to render textures in games or just on the screen on the desktop. But this kind of level of parallelism that was needed to render a texture was super good to accelerate the computation of neural network. So this is basically the kind of the situation that we live in right now, partially happened because of the hardware insight that people had. So right now there are a lot of different architectures that support the inference on the edge hardware. And there are probably big two players in this market, maybe three. So ARM is very big there. And the new architecture that is called RISC-V, that is an open source architecture, is arising more and more in artificial intelligence industry. And I expect that in 5 years from now, we will see an equal amount of RISC-V and ARM devices running in production, running artificial intelligence algorithms in production. And there are also some specialized hardware devices. But the biggest thing that I see in hardware market is kind of the synergy between specialized units that can do matrix multiplication very fast and the commodity architectures that use these specific units as a part of their system on a chip. This is probably the biggest thing that I see on the market. About software, we need to split it into two parts: tools and algorithms. Tools are the libraries and the infrastructure software that we need to build the solution on the edge. And algorithms obviously are about how to create a model. So I will first speak a bit about the tools. So if we speak about the tooling, it is still a very scattered market. So there are a lot of libraries and a lot of different ways on how to train a neural network and how to go on the edge. But typically the process right now looks the following way. We trained a neural network in Python using either PyTorch or TensorFlow. Then we converted using Python into ONNX format. ONNX is a standard that was introduced 5 years ago to standardize the way different frameworks store and infer neural networks. And it's a super big thing. Obviously, ONNX is not perfect. It does not capture all the possible architectures and all the possible new layers that are introduced in all the research papers. But it basically, it makes some structure of the chaos that we see in the industry. And because of that, I'm super thankful for its existence, basically. And after converted to ONNX, their neural network, the algorithm is basically converted to the library that supports edge inference, meaning that it's optimized for the edge devices. For example, if we are talking about mobile devices, you may want to convert it to TF-Lite to CoreML. For example, if you are talking about the video space chips that are provided by Intel, you would convert it to OpenVINO. And the general rule of thumb is if you're working with some hardware, the hardware provider produces some licensed software that is used for these devices. If we are talking about, for example, RISC-V devices, and specifically about Greenways chips, there is a full kind of computer a software stack that you would use, and kind of a preferred way to convert so that you get the highest possible performance on the target device. You can obviously go another way, and you can try to implement it even yourself. But the way that is recommended by the provider of the hardware typically is the most compute efficient and energy efficient. So you will get the best performance per watt and performance in terms of seconds and milliseconds if you go the kind of recommended way. Still, I think that the situation that we are right now is not perfect, and it would obviously be better to kind of have a framework that you would train and infer in. But it turns out that many years have passed, and this is not the case because the hardware providers, they know their hardware better than anyone else, and they are just better suited to create the hardware that create the tooling for their hardware than anyone else. This is it. So this process, even though it has only 3 steps, it's almost never straightforward. You have some caveats here and there. For example, when you convert a network to ONNX, it almost never converts in the first run. If you have some specific architecture, you will have some issues here and there that you will need to go and fix. So the first iteration, you will need to kind of iterate there a couple of times. And then when you go from ONNX to your target framework, you will still have some issues, probably, because it will either not convert, and you will need to fix the ONNX model here and there, or it will convert in non-optimal way. So you will have some extra computations that you will want to get rid of when going to production. So the process is just never straightforward. It takes a couple of days for some models. Okay, I will go to my next slide. I will talk a bit about, I talked about the tools. Now I will talk about the algorithms, the kind of second ingredient to the software when speaking about artificial intelligence on the edge. So neural networks are super redundant. Even though they kind of simulate brain, but our brain turns out to be way more energy efficient and compute efficient than neural networks. And there are some ways to fight that, but not a lot, to be honest. So when we start with a model, it can be very big. So some state-of-the-art models, they are bigger than 1 gigabyte. And they require a lot of operating memory to be inferred. But when we work with compute, very small devices, we don't have this luxury. So we need to compress them. To do that, we basically have 3 options. First, as I already said, we need to start with smaller models right from the start, not compress a big model, but rather start with something small like MobileNet. Then we can apply two different kind of orthogonal methods. First is called quantization, and the second is called pruning. Quantization is about going to smaller bits when you do the computations. For example, instead of computing in floating point numbers, the floating point numbers is not a good option for the edge inference, and they are almost never used, I would say, as is, like 32-bit floating points. And the models are typically converted to something smaller to do the computation in smaller bitness. The options, there are several options. The easiest one is to go to 16-bit floating point numbers. And typically it's the easiest point. In most cases, it just works out of the box. In many cases, though, you need to go from floating point to fixed point. And this is the tricky part. Thankfully, we already have a lot of software that implements this shift without dramatically sacrificing the quality. So now I see a lot of networks that are inferred in 8-bit fixed point or even less. And the most extreme way for quantizing neural network is binary quantization or ternary quantization. Binary is when you have only zeros and ones, and this is it. And ternary is when you have -1, 2. To be honest, these networks are not super popular because it's really hard to create a working solution with them. But if you manage to succeed, basically you have the most optimal way to infer ever, which is great. Pruning is when you cut the network here and there. You reduce the amount of filters in the convolutions in the network here and there. And basically you make the network thinner. The thing is that for many kind of implementations, hardware implementations and software implementations, it doesn't make sense to shrink to something that is not 16, 32, or 64 channels, because the optimizations are written so that the number of channels need to be a power of 2. Otherwise, it goes to the the ceiling of this amount that you have closest to the power of 2. So it doesn't make sense to make 37 layers, 37 channels. You would rather live with 64. Or if you cannot do like 32. Does it make sense?
Yep.
Okay. So basically, this is my last slide. I covered kind of I tried to cover at least 3 kind of big topics: why, how, and the caveats of the artificial intelligence on the low power and edge devices. And I would be super happy to answer your questions.
Thank you very much.
Also, like if you want to reach out, here's my email on the bottom. I would be super happy to answer the question that may arise after the session or just talk. Please reach out.
Thank you. So I have a question on the quantization, because yes, we hear a lot talking about binary, ternary, and sub-byte quantization. Do you see any client in production which is using sub-byte quantization? Because we hear a lot talking about.
So yes, sub-byte. I saw that and I actually implemented it myself back in 2018, and it works in like 10 countries. So I'm sure that it exists. Binary and ternary. I have never seen ternary. I heard about binary, but I haven't touched it with my own hands. So I'm skeptical about that. Like it's like there was always a buzz about that starting from 2015. And all the time it seemed like we just need to do a little something and we will get there. But to be honest, I don't think it is. It is so simple, at least.
Okay, thank you. Then we have another question related to how we can smoothly improve networks. So as you said today, model deployment comes after model training. You see any perspective in future for smoothly and autonomously improving deployed model over time from an hardware, algorithm, and tooling viewpoint?
So I mean, I definitely think it will happen sometime in the future. But to be honest, like it's so much easier to implement, like to create good neural networks with a human in the loop than autonomously. So that, just like as I said, if you have a very good data set and a very good understanding of the problem, you are able to create a very good solution right from the start, so that you will kind of, the effort that you will need to spend to create an autonomous system from that will not be kind of required, will not give you the kind of the amount of like the percents that you will need. That's what I saw from like many companies I worked with. But I do believe that these systems, they are deployed somewhere, they exist, they're just rare. And I do believe that they will appear in some future, but I don't see them, a boom of them happening very soon.
Okay. And then we have another one from Arnab, which is quantization and pruning techniques have some compromise in terms of accuracy. What's your take on making sense of the trade-off between accuracy and network size reduction techniques of quantization and pruning?
Yeah, thank you. That's a very good question. I will go back to my previous slide. So as I said, like, yeah, AI models are highly redundant, but when we start to prune them, when size decreases linearly, the quality doesn't decrease linearly. It has kind of logarithmic nature. So like imagine there is a pruning process demonstrated here, and we started here. We actually go to the left in time, which is not intuitive, but still. So first we had the biggest model size, and like eventually we will just decrease it to 0, right? In this case, what we see, the behavior that we see is you can decrease the model size by half with sacrificing like couple of percents in the quality. There is always some sweet spot on this plot, right? That you will be able to, where you will hit the quality requirements and already dramatically decrease the model size. That's what I see.
Okay, thank you. Then there is another one more general, which is asking recommendation for people that wants to join areas of computer vision, deep learning, and tinyML.
Yeah, thank you for the question. So the absolute best start, obviously, probably is CS231N from Stanford. So this is a pretty hard course, I would say, like even like, especially if you do all the exercises like implementing things from scratch in Python, it's a very good course that will give you a very good background and like kind of fundamentals to go in artificial intelligence. I myself am like, I definitely recommend to start with some fundamental understanding, because if you just go from example to example, just running some, repos on GitHub, which is pretty easy, you will be always limited in development of some well-performant neural networks. So you need to understand the basics. From that, I would definitely recommend the book from Ian Goodfellow about basically neural networks in computer vision. It was published several years back already, but still is very kind of covers the whole industry very well. And after that, I would suggest to start coding as much as you can. And the best way I saw in my kind of area is to start Kaggling or doing some other competitions, which will give you some hands-on experience on of the neural networks, because it sounds really, really well when you read about it in a book, but when you face some stupid bug that you spent 8 hours on, it's a completely different experience. So this is kind of the 3 steps: CS231N, then book, then Kaggle.
Okay, thank you.
I just quickly cover again the sponsors who helped us to organize this event. So Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, Greenways Technologies, Grovity, HOTG, Imagimob, Latent AI, Maxim Integrated, Analog Devices, Kixo, Qualcomm, Reality AI, Renesas, SAP, Seed, tinyML, SceneSense, Sentient. So software and hardware foundation for tinyML, it's ARM. Deep Light, we use AI to make other AI faster, smaller, and more power efficient. tinyML for all developers, so it's Edge Impulse, of course. EMSA, the I in IoT, Edge AI visual sensors. Greenways Technologies, enabling the next generation of sensor and hearable products to process rich data with energy efficiency. Grovity, software development services for tinyML solutions. HOTG, distributed infrastructure for tinyML applications. And I think Latent AI, adaptive AI for the intelligent age. Maxim Integrated, enabling age intelligence. Kixo AutoML, automated machine learning platform that builds tinyML solution for the age using sensor data. Qualcomm AI research, advancing AI research to make efficient AI ubiquitous. I don't know this word. Reality AI, add advanced sensing to your product with Edge AI, tinyML. SenseML builds smart IoT sensor devices from data. SceneSense, Sentient. So thank you again. Thanks to all of you who came today. Thank you, Anna. Thank you, Francesca, for made this to make this webinar so successful. And so we see everybody again in a couple of months. Please stay tuned.